Good afternoon, this is Schweitzer. We're going to do a little video here on orbital quantum numbers. This is piggybacking off of our Bohr diagram video. And then we did one on the electron configurations. Electron configurations. Now, the Bohr diagram only encompasses the principal quantum number. Then just that one. The electron configuration does the principal and the orbital. We're looking for a model that could maybe do both, again, the magnetic and the spin. And that's going to be the orbital diagram, orbital notation. Okay, so how does that work? First of all, okay, what's the spin quantum number? We've done a bunch of these already here. So the s orbital, p orbital, d orbital, f orbital, suborbitals. There's 1, 3, 5, and 7. Maximum electrons would be 2, 6, 10, and 14. So in a suborbital, in an orbital, there's suborbitals. How do we show these? So an s orbital, what it would do is below it, you can put a box like that, representing the suborbital. The naming conventions for the suborbitals can change, and it's not a huge thing, but the typical number would be 0, giving it just like a room number. The p orbital, okay, again, you could put a box like this one, or maybe someone just puts a dash, representing the bottom of the box. Now this guy's got 3 suborbitals, okay, here, and the typical would be number them, which isn't even required for for any notation. Just so you know, just to give them a number like that. You'll find all of the quantum numbers so far have just been letters, but they start as numbers, and we'll show that later in this presentation. A D, of course, is going to be, and these are all lowercase letters, by the way, but have 5. So 1, 2, 3, 4, and then 5. And you notice that inside each one of these particular boxes is suborbital. So the spin quantum number, okay, is typically seen as an upspin or a downspin. Okay. Now, the only thing I know about these is that they're equal in energy, so up is no better than down. So energy really rules everything here. Okay. Okay. So up and down makes a difference, so they can slide into a spot here. So I could put inside of an individual suborbital, okay. If I have an upspin and as an electron, each of these represents a single electron. Then if I put another one in the same suborbital, it has to go down. Okay, and we'll detail that a little bit more as we go along. But all right, so let's try this out. How does it work? So let's do an orbital diagram for boron. I got that written twice here. So let's try one. Apparently I'm going to do boron here. So boron's located right here. Okay. You should be fairly adept at doing electron configurations because we start with an electron configuration. Now you'll go in a textbook, you'll go online, you'll see multiple variations of how this works. They all kind of look the same, just different ways they write it down. This is how I do mine. So boron, what I like about this method is it allows me to convert an electron configuration directly to an orbital notation without changing anything. So it's going to be 1s2, 2s2, 2p1. That's the electron configuration. And then all I do is I put in my orbitals below it. You'll see some books stretch it out to the right. To me, this is more convenient because I can just quickly add it. There's my suborbitals. And of course, you'll see other books that do it this way too. You don't have to add the zeros and ones if you don't want to, but this is full. And it's really going to be full up until the end. And now here's another little thing you might note. Energy-wise, for suborbitals, okay, it's important to realize that the energy of each of these 3 is identical. And since energy is equal to all of them, then guess what? They all are fine. Up and down has the same energy. All the suborbitals are the same energy, so that doesn't matter. pick whichever one you want, and plop an electron in there. I'm just going to do the top one. Why did I choose up? Because I wanted to. Could have chose down. Okay. So with that being said, okay, that's it. Just add your suborbitals, and there you go. It says boron here. Let's maybe try another one here. Let's try. Let's pick. Let's do one that's a little bit more involved. Let's do. Let's do scandium. Okay, SC. Might as well get a D in there. So it's going to be. I gotta get some room here. All right, so it's going to be. All right, let's get some room. Let's just add a quick page here. So scandium, SC. I'm going to quickly run through electron configuration. So you can try this one on your own. 1s2, 2s2, 2p6. I'm just mentally walking the periodic table. 3s2, 3p6, 4s2, 3d1. So I've just walked my mind through the rows of the periodic table until I got to here. And now it's simple. All I gotta do is add in my boxes. Now, again, if you don't want to put a box, just put a dash. That shows these guys. And then, of course, at the end, a student will typically ask me, oh, I got 5 suborbitals, so I got to show them all? Or can I just put one here? You know, it's not that much harder to do just to do this. So I usually just show it so that, you know, you're not leaving any room for error. Someone saying you didn't know something, but there we go. And move along pretty quick here. And which one I pick? I pick this one. There we go. All right, next. All right, so here we go. Orbital diagrams, pretty common here. What about Hund's rule? So we're going to do an example here of nitrogen. Okay, so nitrogen, as you see here, is going to be 1s2, 2s2, 2p3. All right, so what do we do if we have multiple electrons? This is called Hund's rule. So Hund's rule states that if we have multiple electrons in a suborbital, that it's two electrons in separate suborbitals, okay, is lower in energy than one suborbital with 2 electrons in it. And what that means is that essentially they spread out as much as possible before going on to the next, before filling them up again. So if this is going to be nitrogen, it's going to go suborbitals, and all you do is this, and then these guys fill independently first. Okay. Now again, this is nitrogen, so if I want to add another electron on, okay, let's see, so rather than nitrogen, let's do like fluorine. So we're going to add 2 more electrons on here. So we'll do, cross this off, convert it to fluorine. Now I need 2 more electrons. Where do I put them? Doesn't matter. Just match up like that. Make sure they're opposite spins. That's really everything. All right, next one here. Okay, Hund's rule. So again, means that electrons fill separately. Fill suborbitals for, individually first. Now, for pairing. Now, if you look at a book definition of Hund's rule, they're only going to deal with it in terms of energy, which I just talked about. So we just did that one here. Bohr diagram, energy for a Bohr diagram. Okay, so we did a couple of examples of that. Let's move along. All right, quantum numbers. Okay, so like I mentioned earlier, quantum numbers actually are numbers. So let's just kind of highlight that a little bit here. So the n is just going to be 1, 2. This is the only one so far we've had that's actually been a number. 5, 6. Then we have our orbitals. Now that is an s. I have it located right here. The s is actually considered a 0. the P is considered a 1, the D is considered a 2, and the F is considered a 3. And then we have the magnetic quantum number, okay? Now this is the suborbitals, which is I'm showing here, and this is where they give, this is just the number that I listed on the suborbital earlier. So this guy is 0, 0 plus 1 minus 1, 0 plus 1 plus 2 minus 1 minus 2, and the F would just be same thing. And then the spin, okay, is just plus 1/2 and minus 1/2. Now you might even just see them just listed as 1/2. Okay, that's pretty common. I really have never seen them do plus or minus on there because they're the same. Doesn't matter. So every single electron in an atom gets 4 quantum numbers, and they're never the same. It's called the Pauli exclusion principle, but essentially every electron gets a different set of numbers. So if this guy is this set of numbers, that means that this guy right here would also be in the first energy level, S block, same suborbital, but it would be minus 1/2, technically. Okay, what would this one be? So second, now again, this is where this model fails a little bit. We don't know, the Bohr diagram doesn't show us whether it's S or P. So second energy level could be S, could be P. 2 of these are for the S's, and the rest are for P's. So it'd be like 1S, 1N, sorry, second energy level, S block, S orbital. The S only has this guy, that's it. And then it could be 1/2. Now this wouldn't be the outer one, or the lowest energy one. Let's say this guy is the other S. Okay, that would change that guy to a minus 1/2. But let's put this one. It would be second energy level, P block, and now I can pick any one of these I want. They're all legitimate. So 0, and then just 1/2. So, and this would be, all these would be doing, with, again, this one here, technically, okay, the next one would be 2, second energy level, P. Now it's going to use Hund's rule. It's going to fill out a different one. So this one's going to be 1 1/2. And this one right here would be 2 1 negative 1 1/2. Nice. That's a great example of Hund's rule right here. Right? Hund's rule. Filling in individual suborbitals first before matching up. All right. That is going to be a good example of this. Which set of quantum numbers could not correspond to an electron configuration in the ground state of palladium, PD? So finding PD, I guess it's just the only type of example I've really seen of this. So PD, find it, is somewhere here. All right, PB. Here we go, palladium. So this is ending in the, was it the 1, 2, 3, 4, 5th, 5D8. Okay, so it's there. All right, so here we go. So what we're looking at here is, okay, the which could not correspond to an electron in the ground state phase of palladium. Probably should just mention what that means here. Let's do that one. So what does ground state mean? So whenever we're doing configurations, electrons fall to their ground state if possible. If there's room, it falls down to the lowest energy state possible. If you had energy, you could jump it up to a higher one, but then it falls back down again, typically speaking. So we just do the most lowest energy, the most optimal energy method or configuration. So that's called that. Okay, so it's just your standard method. So they're not asking for even a valence, any electron in palladium. So the fact that it's palladium really doesn't really matter that much. It just wants to know, are these legitimate numbers? So second energy level. So this is second energy level. This is P block, and it's P block, and then -1, which is fine. Okay, this one I believe works. Okay, this one, third energy level. All right. Now this would be an F. Okay, so for this, 0 is S, 1 is P, 2 is D, 3 would be F, and there is no 3F. So that's a problem here, and that's really what we're looking at here. We're looking for an illegitimate configuration. This is 4S, and then it's 0. Now again, this has to be 0. S's have to be 0, so that's good, and -1's fine. So that would be just like having my own energy level here. And then fourth energy level, 2 is D, so we'd have 1, 2, 3, 4, and 5, and is on the D orbital 2, okay, that's 0 plus 1 plus 2, that's this guy, and plus 1/2. So all of these work. I'll redo that for this A here. So A was 2P, and then 1, 2, 3, and then of course the -1, that's this guy right here. Okay. All those are good except for B. B is one that's not going to work. So anytime you see something like this, we're looking for just what would be an illegitimate version. All right, which of the following gas phase ions is the largest unpaired electrons in the ground state? Okay, so let's just go ahead and sketch this out here a little bit. So chromium, Cr plus 3, okay, is going to be located right here. So chromium plus 3. Actually, let's do this here. Let's just end this video here, and we'll maybe pick it up later on with some of our practice questions. All we have from here on out is just some practice questions. And I'll let you guys maybe putz on these on your own, but all the content in it for this video is over. All right, thank you very much.